Okay. So when I'm doing now, let's quickly summarize everything and take this as very serious half an hour. The reason being, I'm telling you the process of revision because once you start your preparation and you finish a topic, people ask me many questions, sir. I have finished this topic, and this is actually important question also. How we should revise this? Can you revise? Should I revise entire theory, numericals? Should I go solve gate questions also? And this question become more important when you enter into October, November, December time frame, right? So I feel, and this is my way when I was doing the preparation, how I used to summarize things. So what I'll do is I'll close all the notes and I'll start writing in the sequence in which I have done the topics. Guys, never break the sequence because when a question comes in your exam, right? A good preparation is your mind will directly take you that this is my third topic in axial flow compressor which I have studied. So there always should be a storyline. So if a numerical comes from velocity triangle, I know that my velocity triangle is my third topic. I have done construction, I have done working principle, and then I have done velocity triangle. So it's very easy to recall formulas in those ways. You will never forget anything because now we are talking about only revision of axial flow compressor. In 3 4 months, you will be talking about entire gate syllabus revision, right? And you have to revise entire subject in maybe maximum 2 hours. You will have that much only time because if you do 2 hour revision for one subject, it will take maybe 1 day or 2 day for revising the formula. So this is the best way I feel is for revision, and it is something like this. I'll start with compressor. First of all, tell me what we have learned in compressors. First point. All right, I'll do it. Anytime you feel, add me. I'll add those points here. So what I've learned in axial flow compressors, we have a stage, and a rotor and a stage is nothing but a rotor and a stator is together known as a stage. All right. We have also learned that ahead of rotor blades, we also have inlet guide vanes. Don't write these statements when you're revising on your own. So inlet guide vanes, you should just recall in your mind, they will not do anything to pressure. They will not do anything to static stagnation properties. The only thing is they're going to guide your flow into the system. That's the only thing you need to write when you're revising axial flow compressor so that we know that we are on the right track. I remember everything. Now, when you have written this, what I'm going to do is I'm only writing working here. Now, when you're writing working here, this doesn't mean that you have to write all the statements, but in your mind, you should know that in rotor, you have two functions. One is you hit the air, and second is divergent section. Correct? Then in stator blades, you have only divergent section. This is more than enough. If you understand this, that means you are good in theory. Fourth, definitely you should draw your velocity triangles, but I will summarize now in a different way. So you have rotor blades, you have stator blades, and now quickly tell me what happens to absolute velocity, relative velocity, static pressure, static temperature, stagnation pressure, stagnation temperature, and so on. Tell me what happens to absolute velocity in rotor blades. We'll directly say absolute velocity increases because we hit the air. When we hit the air, my stagnation pressure also increases. Correct? Both of these should be marked together because they are one and the same thing. Then, so this is covered. With divergent section, this velocity reduces and hence my static pressure increases. So these two people go together, and when static pressure increases, static temperature increases, and stagnation temperature increases because work is supplied. We are hitting the air, right? So this is your entire summary of velocity triangles. You can draw your velocity triangles also when you're revising because that's how your gate questions are coming, right? So you should be in a habit of drawing your velocity triangles very quickly. And then let's go to stator. In stator blades, first thing, no relative velocity, only divergent section. Divergent section will reduce my velocity, increase my static pressure, increase my static temperature. Stagnation pressure reduces because of friction. If there is no friction, it will remain constant. and stagnation temperature always remains constant because there is no work. So this is entire summary of your velocity triangles and ideally speaking your enthalpy entropy plot also. Now, because we have already learned enthalpy entropy plot, you know Bernoulli's equation. In rotor blades, Bernoulli's equation followed is H naught 1 relative equals to H naught 2 relative. And in stator blades, Bernoulli's equation followed is H naught 2 equals to H naught 3. So I've covered everything in working velocity triangles, what happens to each of the properties, and we have hardly spent 5 minutes and this is done. I need nod from you people. I know I'm going a bit fast here, but you people need to check me. Please tell me if this is a bit fast. Do you want me to go slow? And you have to do it for each subject. And I will do it for each and every topic from now on. Whatever we are doing, we will summarize this. Maybe it will take one more lecture extra, but this summary is super important for your revision. Now, let's move forward. So we understood construction, we understood working, we understood velocity triangles. Then we derived equations, right? And I will write all the possible equations I have learned in the sequence. So when we started our velocity triangle equations, we started with this equation. U is equals to CT1 plus WT1. Now, might be you people need to see your velocity triangles, but because I have done it so many times, I recall these equations. And this is also equals to your velocity, your speed equation from the exit. And once you break this CA tan alpha 1, from this, we got an expression something like this. I don't know how many of you recall. Tan alpha 2 minus tan alpha 1 equals to tan beta 1 minus tan beta 2. This is our lecture 2. When we started velocity triangle, this is the first thing we developed. After this, we started going into specific work and power. So when we write work, let's start with the very basic equation. We started with Euler's equation, and it was something like this. U into CT2 minus CT1. This was our first expression. Then we can also write this as U into CA tan of alpha 2 minus tan of alpha 1. This is another work. We can also write this as U into CA tan of beta 1 minus tan of beta 2. You also know you can write work as H naught 3 minus H naught 1, which is same as H naught 2 minus H naught 1, because there is no enthalpy change in rotor blades. And you can even write this as CP T naught 2 minus T naught 1, which you know can also be written as CP delta T naught S. And the beautiful part is that all these things are calculated in joules per kg. That means all of these expressions is for specific work. Now, in my exams, if they ask me to calculate power, that means in watts, what I need to do is I need to multiply it with this specific work. Now, again, if you, because this is our summary notes, we know this is specific work and this is power. And you can take work expression of any form. You can take this, and then your unit will be watts. Now, because we have done the entire theory, I will write it here only. 9. If work done factor is given, if in my exams they give me this, use in work equation. I hope this is more than enough note. You need not to learn what diagrams I have given you, blah, blah, because those are the things we were doing to understand things. But now we are doing revision, right? So you have some story in your mind. Work done factor is because your CA was increasing, so you have multiplied a factor. But in your exams, the most thing they can ask is they can give you work done factor and ask a numerical. So I've finished everything they can ask in work. They can ask specific work, they can ask power, they can ask in terms of velocities, they can ask in terms of air angles, they can ask in terms of blade angles, enthalpies, temperatures, and so on. Now, with this connected only, I got another formula that if you know your temperature change, you can calculate number of stages, right? So total temperature rise for compressor divided by temperature rise for one stage will give us number of stages of a compressor. So this is also connected. We know we have calculated temperature rise from here, right? Now the next connection is coming from this only. How do we calculate this? Enthalpy, isentropic efficiency comes into picture, right? And again, no need to derive all those expressions drawing these graphs because this is your revision. So I will quickly write, and you have seen how many questions they have asked on this. I think maybe 10 questions only on efficiency. Gamma minus 1 by gamma minus 1 divided by T naught 2 minus T naught 1. But when you are revising this, you should remember this. This can be used for complete compressor or stage. So this can be stage efficiency or it can be complete compressor. It totally depends upon what pressure ratio you are using, what temperature you are using. So it is possible. With this connection came polytropic efficiency. We have learned polytropic efficiency. So what is polytropic efficiency of compressor? It is gamma minus 1 by gamma into n upon n minus 1. And with this, we can calculate pressure ratio temperatures in this form. So P naught 2 by P naught 1, T naught 2 by T naught 1 equals to P naught 2 by P naught 1 raised to the power. It should be gamma minus 1 by gamma, but now it becomes, if I'm not wrong, n minus 1 by n into polytropic efficiency of compressor. Maybe you people have learned the reverse way. Maybe you have given this power here. Guys, just give me a quick nod if this is fine. I don't have any notes in front of me, so I don't know if I've. This is correct formula only, right? Just don't want to give anything which is. This is not gamma minus 1 by gamma. Correct only, na? No, 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 no. Sorry. My bad. I'm writing gamma, right? Guys. I'm so stupid question. This is gamma minus 1 by gamma into polytropic efficiency of compressor. This was the formula we have derived, right? Correct only, na? Absolutely. Now, I am not writing because I don't recall the formula. Actually, you can write relation between isentropic efficiency of compressor and polytropic efficiency. I can derive it now, but revision should not have derivations, right? I have not learned that formula. But if question comes in my exam, I will definitely quickly derive it. There is no derivation actually. You need to simply substitute the values. So maybe you can write your formula here if you want to learn a formula. No, efficiencies are covered. So don't see, I'm not breaking the sequence. I'm going in the same sequence, guys. Basics, construction, working, velocity triangles, power absorbed, efficiency. Now I'm entering into degree of reaction. So then we have learned about degree of reaction. So we know what is degree of reaction. First degree of reaction is static enthalpy rise in rotor divided by static enthalpy rise in stage. So if you write this as a formula, you can write this as H2 minus H1 divided by H3 minus H1. And in your mind, you can quickly recall that it tells you how much static pressure rise is happening in rotor compared to how much static pressure rise is happening in stage. Because enthalpy tells you temperature, temperature tells you pressure. But the major thing in which we have learned here is in aircraft, we typically use a compressor which is 50% reaction compressor. Which simply means R is 1 by 2. And before going into that, sorry, my bad, we should have written the formula we have learned to solve the numericals, right? It was Ca divided by 2u tan of beta 1 plus tan of beta 2. I told you work expression, if work is negative, this should be positive here. Then we have seen 50% reaction compressor, which was R equals to 1 by 2. And this, we have learned few things here. One, inlet and outlet velocity triangles are symmetric. This was the property, right? And if they are symmetric, then we got this equation. Alpha 1 should be equals to beta 2. That means CT1 should be equals to WT2. And alpha 2 should be equals to beta 1. That means CT2 should be equals to WT1. Then you have in the theory, when I was doing the lecture, I have explained you low degree of reaction, high degree of reaction, but revision doesn't want that because you people are clear what degree of reaction means. So we know what all things we should write in our as a revision, because in the end we need to revise formulas. Theory, when you attended a lecture, right, it will stay with you throughout your life if you understood the concept. And if any theory question comes in your exam, automatically that theory point will be recalled in your exam. So don't worry about revising theory points. Whatever you have written important points, that is more than enough when you are attending the lecture. Then please neglect this. Once this is done, we entered into small topics of compressor. So we have understood performance coefficients. First, we have seen flow coefficient, which was Ca by U, correct? And the advantage of this is that it controls the stalling characteristics of the compressor. The second coefficient we have seen was work coefficient. This is also known as loading coefficient or temperature drop coefficient. And this was work divided by U square. And then we know you can write it as U into CT2 minus CT1. You can write it in terms of many form. Any work formula, what you have learned, it can be written in that form. And you have seen this is also asked in your exam, right? Now, once these performance coefficients are done, now I got a hint for my next topic, stalling. So don't write all the blah, blah, blah theory we have learned. We know one thing. Recall in your mind, close your eyes and think whether you have recalled everything. So stalling is basically flow separation. And in this, we have seen two kind of stalling. One is design. Then you have low mass flow rate. That means low Ca. Can you people tell me what kind of stalling is this? When you have low mass flow rate, low Ca, what happens to incidence? What happens to your angle? Incidence increases, right? And when incidence increases, what happens? This is known as positive stalling. And positive stalling happens on suction side. Then we have studied high mass flow rate condition. That means high Ca. High Ca means incidence decreases. That means negative stalling. That means this happens on pressure side. So in 2 minutes, you have revised everything about stalling. You should not even touch your entire paragraphs in your study material, which I have given, not required. After stalling, we entered into surging. And again, don't read during the revision the entire thing. What you just need to quickly recall the surge graph. So on this axis, you were having mass flow rate. Even if you forgot this under root T naught, P naught, it's okay. Here you are having pressure ratios. And your graph was looking something like this for a particular speed. If your speed increases, your graph is something like this. If your speed reduces, your graph is something like this. And this was our surge line. So with respect to mass flow rate, you can check what answers questions they are asking. So if you want, you can give it a read. If you're not able to recall, then give it a read how I have defined this plot from this to this to this to this to this. And guys, any topic we forgot during our revision, don't stop your revision there. Leave it, move forward, open your notes, open your video lectures portal, read it again, see the video again, and then close it. Next time when you come to this revision, right, you will not forget this topic also. I will tell you what happens in the end. Then last, we have seen enthalpy entropy plot. Nothing to write here because whatever takeaway was from enthalpy entropy plot, right? We have already written here. See, the whole thing we have done today, the summary was this. That's it. So, guys, revision is very short and sweet. We should not learn the whole lecture. We should take away. My target is to make you understand things in such a way that you can finish your revision in this way in a very short time. Then close your eyes and think, have we missed anything? So construction, working, velocity triangle, absorption, this, blah, 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 blah. This is all what we have done. Then we have solved all the gate numericals. We are not going to revise gate numericals daily, right? And last but not the least, some important notes. Now, this is not revision, guys. This is last ending from my end on compressor. I want to give you some points. If you see my older videos, I have also taken a lecture on free vertex principle, but this time I'm planning to take free vertex principle in turbine because it is used only in turbine in reality. In books, might be they have given in compressor, I don't recall, but it is never used. I'll explain you the concepts now slowly and I will answer many of the theory questions. So first, can you people tell me in compressors what kind of blades we use? Are we use normal plates or airfoil shaped blades? Airfoil shaped blades. Okay, good. Next question to all of you. Are these airfoils highly cambered or less cambered? Highly cambered. Less cambered, right? And why they are less cambered? No, no, Nikita. Come on, Nikita. Less cambered only, right? Come on. And why these airfoils are less cambered? Why in compressors you use less cambered airfoils? To avoid flow separation, that is stall. So you should write these points quickly in your revision. So first, blades are airfoil shaped, comma, less cambered compared to turbine blades. And why this is? And I am writing it for your notes, but when you're doing your revision, right, you will only think this in your mind. Airfoil shaped blades, less cambered compared to turbine because of adverse pressure gradient and to avoid flow separation problems. So you will not write this in your revision when you're doing in your rough. In your notes, it should be present because of adverse pressure gradient, which will cause stalling. And we know stalling is nothing but flow separation. Second, tell me what happens to length of the blade when the number of stage increases. What is happening to the length of the blade when the stage increases? So my point is this. If you have a compressor something like this is the shaft, this is the rotor hub, Correct? Your first stage compressor will look of this length. Then your next stage is this. Then your third stage is this. And then your fourth stage is this. Definitely you have stator blades also. But when the flow crosses or move from 1 to 2 to 3 to 4 stage, the height of the blade decreases. So like that point, blade height decreases as number of stages increases. Think about this. What is the reason? Guys, why you are doing this? Can anyone tell me what is the reason behind this? Yes, yes. So keep one thing in mind. When you cross your first stage, you have already compressed your air, right? So why you need bigger volume? When you cross the second stage, you have further compressed the volume. So why you need bigger volume? So in first stage, your air was this, second stage, it is this, third stage, it is this, fourth stage, it is this. So why we want bigger space? And this is the reason we keep on reducing the volume. See, air is passing only in this area. Then air is passing in this area. Then air is passing in this area. Then air is passing in lesser area. Then air will be passing even less area. So the length or the height of the blade decreases as number of stage increases to compensate for the reduction in volume. So we know this also that why, and this is the reason, this is the explanation now. Whenever you draw any compressor, right, in any book or even if you draw in your notes, you draw your compressor like this. So this is turbine, forget about it. This is compressor. And you draw your compressor with this decreasing area, right? It is because the compressor behavior is something like this. That means it is decreasing the volume. Compression is happening. So you know about blade height. Now, just think in your mind, uh, why axial flow compressor has many stages? You need not to write this. This is only in your mind. Compressor has many stages because of adverse pressure gradient. We cannot have it in one go, right? And then you can have these questions in your mind. Why the compressor is used, why rotor and stator, why airfoil shaped blades, why many stages are used, why it is used in faster moving engines. I already explained it. It is because its frontal area is less and hence it has less drag. The only question I have not answered in compressor is this: why the blades are twisted from root to tip. And guys, don't think that I'm not answering this. I will use this theory, free vertex principle, and I will answer this theory with the help of free vertex principle in axial flow turbine. So it will be absolutely clear. Don't worry, it's a linked topic. And I want to give you one final note from my end. Okay, I want to give you a few more notes. So, third point. Can you people tell me if you need to calculate mass flow rate at any position, which velocity you will use, guys? If you want to calculate mass flow rate at the entry of compressor, which velocity you will use? Come on, Abhishek. I think this is a typo. I know you know this. Rho A C A is the velocity which will be used. Manizul, you are writing CA or C1? Absolute velocity is used, not absolute, axial velocity is used to calculate mass flow rate. Keep this in mind. All right. And the next note, and I'm marking this as star because this is might be new for many people. So you know what is blade speed, right? This is U. And you calculate this in excuse me, you calculate this in meter per second. We have solved many questions for blade speed in meter per second. I want to give you one important note here. Although this is very detailed in free vertex principle, but I want you people to know it now also because I have framed many questions on this concept. So this is our, and this is last guys from my end. Then we will close this exim flow compressor. This is the shaft which is rotating. Correct? On this shaft, I'm just mounting my blade. So there is a rotor hub, but just for easiness, I'm mounting my blade here. Just for your understanding. All right, one blade, let's say second blade, and so on. Don't worry why I'm not reducing the length. Don't worry about it. Now, please listen to me carefully. First thing, everything in compressor is measured from this axis, the shaft on which your compressor is mounted. So this is zero for us. All right. Now, if you go to the root of the blade, so root, let me write there only why I'm writing it here. This is known as root of the blade. This is also known as hub of the blade. So root or hub are one and the same thing. This portion is known as tip of the blade. And this is blade height h. You have seen, and not in one single gate numerical they have asked this, but I feel this is because in turbine you cannot neglect this. So in turbine this is super important, and it is important in compressor also in real life. But in gate they are not going in that depth, so they are avoiding free vertex principle, and even in books they have not touched free vertex principle in compressors. Now this shaft is rotating, and let's say it is rotating at n RPM. Now you need to understand the units. N is given in RPM, revolutions per minute. So typically they'll say shaft is rotating or rotor is rotating at 10,000 RPM, 20,000 RPM. Guys, RPM is useless for us. Why? All my velocity triangles are in terms of meter per second. I need velocity. I don't need revolutions per minute. So the only note I'm trying to give you is velocity u, which is in meter per second, is calculated as pi dn divided by 60, where n is in RPM. So if in your exam they give you rotational speed in RPM, you will first convert this into meter per second using this formula. Now the question is, sir, what is this D? So guys, you understand this now. Most of the in your gate numericals, you have seen this keyword. So I can calculate my U at root. Then I have to use my root diameter n divided by 60. And your root diameter, this is root radius. You need to multiply it by 2. I told you every radius is calculated with respect to axial points. So if you take this radius multiplied by 2, you will get your root velocity. Similarly, I can calculate my tip velocity, which is pi d tip into n divided by 60. But now d tip is, this is radius of tip, and you need to multiply it by 2. You will get velocity at tip. And similar way, people don't like doing this in compressors. So maybe now if you see a gate velocity, gate questions, right, you will find the word mean a lot. Mean velocity triangles. Mean is kind of an average in between. So this is mean radius. Keep this in mind. This is not degree of reaction. This is mean radius. And if you use your U as pi d mean into n divided by 60, you will get your mean blade speed, which you people must have seen in every gate numerical. Now I am closing this so that this is also answered that what do you mean by mean. But guys, one question before opening for doubts. Can you people tell me out of these three velocities, which one is the highest? U tip, because diameter is bigger, right? This diameter at tip is the highest. So U tip is highest. Diameter at root is least. So U root is least. And mean is an average between the two. But now if you go to your work formula, guys, you without any question, you never thought about U1 and U2 as different. What you thought? U is a velocity which is blade speed, which is constant. We never thought about that there is a possibility that U might also change. So if you draw your velocity triangle at root, if you draw your velocity triangle here, it will have different U. And if you draw your velocity triangle here, I'm talking about this blade, you have different U. So to avoid that, we don't do any of this, at least in our gate syllabus. What we do, we design our compressor at mean. So without any confusion, they will give us U mean. So they can give you U diameter. This is the only note I want to give you. If someone gives you RPM, please don't feel that you have not studied this. Quickly convert that RPM into meter per second. Similarly, if they don't give you in RPM, if they give you in radians per second, you can use this formula V is equals to R omega, where omega is in radians per second. This is in medium per second and R is the radius. So omega, if given in the exam, multiply it with R again, you should use R mean. So let me write this as small r mean. So you should use this radius here and calculate the velocity. Once you know the velocity, we have solved n number of numericals on this concept. So this is everything from my end. I think I've covered each bit of it of compressor, not even a single point remaining. Tell me, guys, I need your nod here. Then I'll give you some important points on this, not related to technical, another important points. Some homework for you people. This is absolutely clear for everyone. Okay. We will see. When the test series comes, Nikita, we will see. I am not discussing any test series questions because that's our next target, right? So I'm coming to that, what I expect from you people. So now the thing is this. One thing I expect you people to do is, before going into your test series, is to solve these two questions. Okay, it is not present in this PPT. But you need not to take any snapshot because these are the two questions I have given in your study material books. These are lengthy questions. All right. Now, what I expect you people to do before closing this, no, drum type and cylindrical type, Nikita. Nothing else. Entry type only. So, guys, this is question number one, which I want you people to solve in your notes. If you want solution, this is present in your study material books. And another important thing is that this is present in your videos also. So I am not doing this now in live class because I want you people to give it a try yourself. But first thing is it is present solved example in your study material books. Second, it is present in the video portal with my explanations. Question one, don't take a snapshot, it is present. And question two, this is again present in your study material books. And There is a separate video on this in your video portal. I'm not sure about question one, about the video, but question two is present definitely. So you can, I suggest go for the video on this, because if you're not able to understand, ideally speaking, you should solve everything. Now, this numerical is bit complicated. Why? In this, we need to calculate stage pressure ratios also. I think if I'm not wrong, it's a three-stage compressor. So in this numerical, you have to calculate stage one pressure ratio, stage two pressure ratio, stage three pressure ratio separately. And then you have to calculate overall pressure ratio. You have to also have to calculate blade height. So you will learn a lot. Never asked in your gate exam. We have already seen all the gate questions, but let's go to the next level. If they ask, you should able to solve it. Solve these two questions. This is your first task. I already told you study material books or video portal is the solution. I'm not going to delete the video. I'm going to put the video after this lecture. So I will maintain the sequence. All right. And then I want all of you to appear for AFC test in your test series portal. Do this. Try to do this by Monday. I'm not asking you much things. Two numericals and a 20 question test. Prepare solution for this test, keep it with you in your notebook, and we will happily move to axial flow turbine. Guys, believe me, this is the best time to enter into axial flow turbine, because mostly on Monday itself, when I start axial flow turbine, 60 to 70% of your turbine will be over. I think not 60 to 70, maybe more than that. Only gate numericals will be remaining. I hope I am absolutely clear. You people are clear with your next tasks also, what you need to do for the next 2, 3 days. Tell me, guys, are we good?